let me just double check the sound here. Sorry about that. Yeah, if you wouldn't mind. Okay, we've got sound. We're good. Okay, so one of the things that are going to be on your test would be section 3.5, which is implicit differentiation. And, you know, this is kind of a challenging little topic for people, so I wanted to go over a problem from that. We're going to find the slope of the tangent line to this curve at the point 2, 1. Now, I'll do this again here. I did a lot when we were working with this stuff when we covered 3.5, and that is when you're differentiating this equation, we're going to differentiate with respect to x. You need special care when you're differentiating these terms in y. You have to differentiate implicitly, so you're going to end up with a dy by dx term when you differentiate those. So let's take the derivative of the entire thing there. So let's do d by dx. Now, when you're differentiating terms that are a function of x with respect to x, you don't have to use the chain rule. You don't have to do implicit differentiation. It's just the normal thing, so it's 2x. But here, what rule do I have to use to differentiate this one? Product rule. Good. So it's going to be 2 times the derivative of x, which is just 1. So 2 times y plus 2x times the derivative of y. What's that going to be? dy by dx. Good. Plus. Over here, for this one, it's going to be the derivative of the outside. So it'll give me 8 times y to the first power times what? Times dy dx. I wish I didn't write that y to the first power there because it looks like y prime. It's not. Dy by dx. And, of course, that would equal 0. So let's clean this up a little bit. These terms that don't involve the dy dx, I'll move to the right-hand side. These terms that do, I'm going to factor out the dy dx. So it's going to be 2x plus 8y times dy by dx. That's just factoring out. Yeah, I could factor out the 2. Probably not a bad idea. But we'll handle it when we get to the other side. And then divide. Dy by dx equals negative 2x minus 2y over 2x plus 8y. And you're right, Spencer, we can factor out a 2. 2 times negative x minus y over 2 times x plus 4y. And then, of course, the 2's cancel. You should probably do at least a modest simplification. I might be a little unhappy if you didn't divide out the y. So dy by dx. Now the last part of it is to simplify this, and that is to not simplify, but to plug in the point 2, 1. So dy by dx at the point 2 and 1. Let's see, it's going to be negative 2 minus 1 over 2 plus 4 times 1. Gives me negative 3 over 6, or slope of negative 1/2. Okay, looks good there. So the big thing here was that you had to use the product rule and the chain rule as part of the derivative. Yes, sir.
I'm sure it's something simple, but I do this thing y when you use the product rule. Is it 2y versus 2?
So it's derivative of the first. So derivative of the first, I'm looking past the 2 and differentiating the x. So derivative of x is 1. So 2 times 1 times y, that's the derivative of the first. Plus the derivative of the second. So I have my 2x times the derivative of the second, and that's where I get the dy by dx term. Yeah, I did the product rule without showing the work. Yeah. All right, so how are we looking on that one? Okay there? Let's try another one, and it kind of relates to implicit differentiation. In fact, I think it's probably in like the next section, section 3.6, problem number 45. And I'll probably make it a little bit easier than it is in the book, so let's just go with y equals x to the sine of x. Now this is in the form of f of x to the g of x. You can't differentiate this by bringing this down and subtracting 1 from the exponent. You're kind of stuck. I mean, this one's kind of a pain, but there is one nice little trick that we can use, and I would recommend that you use logarithmic differentiation whenever you have something where your rules of logarithms help you out in terms of simplifying the problem before you differentiate this. So if I'm going to find the derivative here, first thing I'll do is I'll take the log of both sides. ln of x sine of x, or x to the sine of x. And you want to use the properties of logs to kind of get things going here. So I'll bring that sine of x out in front. And gosh, it looks like a whole lot messier than it was, right? We've got sine of x times ln of x. Yeah. And now we got to differentiate that. Feels like we're going from bad to worse. So we're going to d by dx of the whole thing. So this is a nice follow-up to our implicit differentiation, because when we differentiate this part right here, what rule do we have to use? We're going to use a chain rule. We're going to differentiate implicitly. So what's the derivative of ln of y? Good. So it's 1 over y times dy by dx. And on the right-hand side, what joy do we get to do over there? Product rule, yeah. Yeah, absolutely. So derivative first, which would be cosine of x times the second, plus the first times derivative of the second. Derivative of ln of x is 1 over x. Now there's not any simplification here. So, all right, bummer. But I can simplify the left-hand side a little bit. I want to get rid of the 1 over y. What's going to accomplish that goal? Multiply by y on both sides. Good. So on the left-hand side, I'm just left with my derivative, dy by dx. On the right-hand side, I get this. You could just write it as sine x over x. It might be better. It'd be times y, but let's save ourselves a little step here. Instead of multiplying by y, what else could I write here? Times, thank you, x to the sine of x. All right? And there you go. You're all set on that one. You could write it as, yeah, exactly that, cosine of x, ln of x, plus sine of x over x, x sine of x. Yeah, might be a little bit better like that, but beyond that, that's not going to simplify at all. Yeah. You know, either of these two would be fine. I mean, I'm not going to be really fussy about writing it as sine x times 1 over x or sine x over x, as long as you get here someplace. The one consistent mistake that people make is that they just put times y here. They forget to go back and figure out, oh yeah, y was equal to x sine x, or x to the sine x. Yeah, they leave the y in there, and I'll probably take off a point, maybe, I don't know. You know, if my favorite teams are winning, I might just write a smiley face and write whoops, you know. So just root for my favorite teams. It's an easy call. You know, I'm not going to do this one out, but another example of a place where you could use logarithmic differentiation would be problem number 41. Y equals the square root of x minus 1 over x plus 1. If you took the natural log of this, what I'd probably do to start with is use all my properties of logs that I can. So the 1/2 is going to come out in front. 1/2 ln of x minus 1 over x. It should have been plus 1. X plus 1, like that. And then you can use the quotient rule here. So you end up with 1/2 ln of x minus 1 minus ln of x plus 1. And now these terms have gotten a whole lot easier to differentiate, because the derivative of that's just going to be 1 over x minus 1 times the derivative of the inside. Let's not forget that. What's the derivative of the inside, Derek? 1. Yeah, so you're in good shape there. It's a lot easier to differentiate this. Could you do it without doing that? Yeah, but I wouldn't want to. Yeah, it'd be such a pain to do it the other way. I wouldn't do it. All right, at least not willingly. Okay. Let's do a Newton's method problem. So that's section 4.8. Now, typically speaking, Newton's method is used to find. Let me just see what's going on here. There we go. Typically speaking, Newton's method is used to find where something equals 0, but you could also use it to solve where two things are equal to each other. I think we did we do one like this in class the other day? This is section 4.8, so it's on page 349. I think we did this one in class, right? All right. So maybe it's not a bad idea to let's see which one would be friendly. Let's do problem number 20. Yeah, that's a good one. ln of x equals 1 over x minus 3. Ln of x equals 1 over x minus 3. So if I'm going to use Newton's method to solve this, then I've got to rewrite this as ln of x minus 1 over x minus 3 equals 0. And now this serves as my f of x. And when I find where f of x equals 0, that's going to be equivalent to finding where these two functions are equal to each other. So, okay. Now, one of the things we're going to need in using Newton's method is the derivative. To differentiate this, I might want to think of this as x minus 3 to the negative first power. Why does that help in differentiating this? Yeah, so you don't have to use the quotient rule. You're just going to use the chain rule. It's going to be a lot faster. So this is going to be 1 over x. That'll actually end up being a plus, right? Because the negative times a negative will be a positive. X minus 3 to the negative second power times the root of the inside. But as Nash pointed out, the root of the inside is 1. So, okay. Let's plug those two things into our calculator and take a quick look at it. Okay, so ln of x minus 1 divided by parentheses x minus 3, or you can put x minus 3 to the negative first power, it doesn't matter. And then 1 over x plus x minus 3 raised to the negative second. Now, probably not a bad idea to look at the graph and try and get an idea of where this graph might cross the x-axis. But I want to look at the function. I don't want to look at its derivative. Looking at the derivative is going to confuse me. So I'll shut off that graph by coming over here to that second equation and just pressing the enter key. So the equation is still there. We can still work with it. But now I want to see the graph. the question is, where do I want to graph this? Well, I don't know exactly where to set my window. Let's remind ourselves about one thing about the log function. Log function is only defined for x greater than 0. So whatever I set my window to, well, I'm going to set it starting at x equals 0 to, I don't know, let me guess up to 6. I don't know what to set the y window to, but you know what? I don't have to. Once I've set the x window, what's the trick? Zoom 0. All right. Zoom 0. And it's thinking about it, and there you go. So, looks like there's a couple places where this is true. Let's just practice finding one of them. Let's find that first root here, near x equal 1. So, near x equal 1, that'll be our initial guess. Okay? We good with that initial guess? Don, something about that that's not looking good for you? Did you guys have the same graph coming out as mine? Okay. All right. So let's take 1 and store it in x. So the store key is right to the left of 1. Store in x like that. That's our initial guess. We need to store that. But then we're going to take that initial guess, x, and modify it. And the way you modify it is you subtract the value of the function divided by the value of its derivative. And we can put those in this way. You hit the vars key, right arrow, and press 1 twice. So that's the function divided by, and then I want to do the same thing to get the derivative. So the vars key again. So the vars key to the right once for vars. Press 1 and then 2. Don't press the enter key yet, because the way that this thing works is if you update the x, then it'll just continue automatically. Store back in x. There you go. And you just keep on pressing enter. And pretty soon you should see that there's really no change in one value to the next. So, yeah. It took us only, like, what, 4 iterations before we converged to the exact value. That's pretty good. Say again?
How quickly does the accuracy go up?
The accuracy converges what's called quadratically. So if you're to look at a lot of these things, what you'd see is the error might start out as like 0.1, then 0.01, and then 0.0001, so it's going to square, and the next one's going to be 8 digits, so 1, 2, 3, 4, 5, 6, 7, 8. So yeah, it's doubling the amount of digits of accuracy each time. So if this is the error, then that's the typical progression. So it's called quadratic convergence. All right. So let's see here. Overall, the answer is x is approximately 0.653, call it 1. You can check that, by the way. You can check that you got it right, because we should be able to do ln of x on one side, ln of x here, and compare that to 1 divided by parentheses x minus 3 on the other side, and wow, we get the exact same thing both times. So it's nice that you can double check your work like that. All right. Here's something else you can expect in the exam. Lots of derivatives, lots of derivatives, lots of derivatives, lots of derivatives. All right. So let's practice a couple derivatives here for us. So a couple derivatives. If you had f of x is e to the x squared minus x. Well, what would happen to f prime? What's the derivative of e to the u? It's e to the u times derivative of u, right? So it's going to be e to the x squared minus x, thank you, times 2x minus 1. So, wow, wait a minute.
That was easy.
Yes, cool. Perfect, perfect. Let's see, you should expect some chain rule ones. E to the 3x, sine of 5x. That's a good one. It's actually chain rule and product rule. So we'll call this one g of x. So this is nice. You get the chain rule and product rule all wrapped into one. That's good. Yeah. Let me just kind of crank this one out and then pay lip service to at least one more problem. So it's going to be derivative of the first, which would be e to the 3x times the derivative of the exponent. So we'll write it as 3 e to the 3x times sine of 5x. So that's the derivative of the first times the second, plus the derivative of the second, which would be cosine of 5x, times what? Times 5. That's the derivative inside. And then we have times e to the 3x again. You could clean this up a little bit by factoring out e to the 3x. If you had to solve for something, say set this equal to 0, it'd probably help out to have the e to the 3x term factored out. 5 cosine of 5x, like that. You know, I guess it depends on what I'm asking. If I'm just asking for the derivative, I guess that's the derivative. I mean, factoring out the e to the 3x doesn't really clear things up or simplify things too much. So I'm not going to worry about that. But like I said, if you had to work with it, then you probably want to work with this setting equals 0. Because if you had to set this equal to 0, it's one of these things equals 0. This never equals 0. So you just end up solving here. And, well, you wouldn't have to quite use Newton's method there, but you could actually use Newton's method to solve that one. All right, one last one. We'll do a related rates problem. Oh, yeah. Things that could cause Newton's method to fail would be the derivative could be 0 at some point in your iteration process, or your initial guess is too far away. That'd be another problem that you could run into. Yeah. Well, I mean, with the orthographic calculator, it shouldn't be that hard to get a good initial guess. Okay, so sometimes it can converge to the wrong point because there might be two roots that are close to each other, so it could accidentally converge to the wrong point. And again, you know, I guess the reason I didn't list that separately is because it feels like you had a bad initial guess. I mean, it's kind of the same problem, but you could list it differently. So implicit differentiation is going to be a big part of working with related rates problems. Gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute, and its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. So the diameter and the height are always going to equal. How fast is the height of the pile increasing when the pile is 10 feet high? So, all right. One of the things that I would give you on this is the volume formula for a cone. So the volume of a cone, I guess you probably should write it, depends on a couple things, V of R and H. It's going to depend on two things. 1/3 pi R squared H. That's the volume formula for a cone. Basically, it's 1/3 the volume of a cylinder of that same height. But they tell us something here, that the diameter of this pile is always going to equal the height. So it's growing in such a way that the diameter here always equals the height here. So D equals H. But let's think about something else here. Yeah, the diameter is twice the radius. So D equals 2 times R. And if I put that in here for the diameter, 2R equals H, then I can simplify this and have an expression that just depends on the radius. And that'll be helpful for us. So 1/3 pi R squared times 2H. 2R, sorry. Thank you. So it gives me the volume, depending just on the radius now, not on the radius and the height, is going to be 2/3 pi R cubed. Nice. Bless you. That's a 2R. Yeah. 2R. Sorry about that. 2R. Now let's take a look at what the problem gives us. It says that gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. That sounds like a rate to me. Feet cubed per minute. What rate is that? dV by dt. Good. It's going to be dV by dt. And they tell us they want us to know how fast is the height changing if the pile is increasing when the pile is 10 feet high. So I want to know when the pile is 10 feet high. So if the pile is 10 feet high, what's the radius at that point? Yeah, because 2R equals H. So if this is 10, then R is 5. So R equals 5. I think I've got all the information I need or can get out of this. So let's differentiate this relationship with respect to time. So dV by dt equals 2/3 times pi times 3 R squared, but that's the root of the outside, times dr by dt. Nice thing is that this cleans up a little bit. The 3's cancel, so I'm left with 2 pi R squared dr by dt equals dV by dt. Let's plug in our knowns and solve for our unknown. So it's going to be 30 equals 2 pi times 5 squared dr by dt. So 2 times 5 squared is going to be 50. So I have 30 over 50 pi equals dr by dt. And yes, you can simplify that by dividing out the 10. So it's going to be 3 over 5 pi is dr by dt. But the problem asks us, how fast is the height of the pile increasing when the pile is 10 feet high? So what are they asking for in symbols? dH by dt. We know what dr by dt is. Let's go back up here. What's the relationship going to be between dH dt and dr dt? Yeah. So we'll get 2 dr dt equals dH dt. So if I multiply this by 2, I'll end up with 6 over 5 pi equals dr dt. And the units would be in feet per minute. Matt? because what we ended up with was dr by dt, but the problem was asking for dh by dt, how the height is changing. So I took this little relationship up here and I differentiated with respect to time. I find out that dh by dt is twice dr by dt. So that's why I had to multiply by 2. Okay, that's all we got time for. Good luck. See ya.